A long, long time ago, in a vast and silent universe, we looked at the stars and thought our Earth was unique. But the James Webb Space Telescope changed everything. It is our eye on the deep sky, looking at worlds trillions of kilometers away, searching for signs of air, clouds, and maybe even the ingredients of life in their atmospheres. Each image it captures is a whisper from a distant place. As you prepare to sleep, this video takes you on a journey of over 2 hours through these mysterious worlds, guided by the sounds of the cosmos. What are these distant planets really hiding? Subscribe to the channel, leave a like, and comment which part of the world you're watching from. Settle in and relax, let's begin. Have you ever wondered what technological marvel allows us to peer into the atmospheres of planets trillions of miles away? The James Webb Space Telescope represents humanity's most ambitious attempt to unveil the secrets of distant worlds, and the technology behind it is nothing short of revolutionary. The James Webb Space Telescope, often simply called Webb or JWST, stands as the pinnacle of space engineering, dramatically surpassing its famous predecessor, the Hubble Space Telescope. While Hubble revolutionized our understanding of the cosmos, Webb takes this exploration to an entirely new level. The most striking difference is immediately apparent when comparing their primary mirrors. Webb features an impressive 6.5-meter primary mirror, more than 2.5 times larger than Hubble's. This isn't just a matter of size, it's about light-gathering power. A larger mirror collects substantially more light, allowing Webb to observe objects that are much fainter and more distant than anything Hubble could detect. The primary mirror itself is a technological wonder. It consists of 18 hexagonal segments made of beryllium and coated with gold. This unusual honeycomb design was necessary because no rocket could launch a single mirror of this size into space. Engineers designed these segments to fold up for launch like the petals of a flower, and then unfold with incredible precision once in space. Each segment can be individually adjusted by the motors with accuracy finer than a human hair to create one perfectly aligned optical surface. Unlike Hubble, which primarily observes invisible and ultraviolet light, Webb is optimized for infrared observation. This distinction is crucial for studying exoplanet atmospheres. Infrared light can penetrate cosmic dust clouds that block visible light, and it's particularly effective at detecting the heat signatures of distant planets and the molecular composition of their atmospheres. This infrared specialization required entirely new technologies to be developed, as Webb needs to be kept extremely cold to detect the faint heat signatures from distant objects without interference from its own thermal emissions. To achieve this necessary coldness, Webb operates approximately 1.5 million kilometers from Earth at what astronomers call the second Lagrange point, or L2. At this special location, the gravitational forces between the Sun and Earth create a relatively stable position where Webb can maintain its orbit with minimal fuel consumption. This distance isn't just about stability, though, it's primarily about temperature control. Being so far from both the Earth and Sun allows Webb to cool down to the incredibly low temperatures required for its sensitive infrared instruments. Perhaps the most visually distinctive feature of the telescope is its massive sun shield. About the size of a tennis court, this 5-layer shield is thinner than a human hair, yet provides sun protection equivalent to wearing sunscreen with an SPF of 1 million. The shield blocks heat and light from the Sun, Earth and Moon, allowing the telescope's instruments to cool to minus 233 degrees Celsius, just 40 degrees above absolute zero. This extreme cold is absolutely essential for Webb's infrared detectors to function properly. The development of Webb's sophisticated instruments pushed the boundaries of what was technologically possible. The near-infrared camera, NIR-CAM, near-infrared spectrograph, NIR-SPEC, mid-infrared instrument, EMIRI, and fine guidance, sensor, near-infrared, imager and slitless spectrograph, FGS, NIRISS. Each represent the most advanced instruments of their kind ever create. These instruments work together to provide unprecedented capabilities for imaging distant objects and analysing the chemical composition of their atmospheres. The journey to create Webb was neither quick nor easy. The project represents more than 30 years of development, with numerous technical challenges, budget reassessments and timeline adjustments along the way. Thousands of scientists, engineers, and technicians from 14 countries contributed to its creation, making it one of the most complex international scientific collaborations ever undertaken. The total cost exceeded $10 billion, reflecting both the ambition of the project and the cutting-edge nature of the required technologies. When Webb finally launched on December 25, 2021, atop an Ariane 5 rocket, it began a nerve-wracking deployment sequence that involved hundreds of potential points of failure. The successful unfolding of its mirror and sun shield over the course of 2 weeks represented one of the most complex engineering operations ever performed in space. Unlike Hubble, which could be serviced by astronauts, Webb's distant location means repairs are impossible. Everything needed to work perfectly the first time. The telescope's revolutionary capabilities are particularly evident in its study of exoplanet atmospheres. Previous telescopes could detect the presence of exoplanets and make broad determinations about their size and orbit, but Webb can analyse the actual composition of their atmospheres in unprecedented detail. By observing how starlight filters through an exoplanet's atmosphere during a transit, when the planet passes in front of its star from our perspective, Webb can identify specific molecules present in these distant worlds. This capability has profound implications for our search for potentially habitable worlds and possibly even signs of life beyond Earth. Webb can detect water vapour, methane, carbon dioxide and other molecules that might indicate habitability or even biological activity. Its sensitivity is so great that it can analyse the atmospheres of relatively small rocky planets, the type most likely to be similar to Earth, something no previous telescope could achieve. The James Webb Space Telescope represents a technological revolution that extends far beyond astronomy. The engineering challenges overcome during its development have pushed forward materials, science, optics, cryogenics, and precision manufacturing. Technologies developed for Webb have applications in fields ranging from medicine to communications to energy efficiency. Like many ambitious space projects before it, the technical innovations created to solve Webb's unique challenges will continue to benefit society in ways we may not yet fully appreciate. As Webb continues its mission, peering into alien atmospheres and unlocking the secrets of distant worlds, it stands as testimony to human ingenuity and our unquenchable curiosity about the universe. Each new discovery not only expands our understanding of exoplanets, but also demonstrates the remarkable power of the revolutionary technology that made such exploration possible. How spectroscopy reveals the composition of alien atmospheres. Imagine being able to determine what gases exist in the atmosphere of a planet trillions of miles away or without ever leaving Earth. This seemingly magical ability is made possible through a powerful scientific technique called spectroscopy, and it forms the foundation of how the James Webb Space Telescope investigates alien atmospheres. Spectroscopy is essentially the study of how matter interacts with electromagnetic radiation, such as light. When it comes to exploring distant exoplanets, this technique becomes our most powerful tool for understanding worlds we can never visit physically. The fundamental principle behind spectroscopic analysis is deceptively simple. Different atoms and molecules absorb and emit light at specific wavelengths, creating unique patterns that serve as chemical fingerprints. By analysing these patterns, scientists can identify the specific elements and compounds present in an exoplanet's atmosphere with remarkable precision. The process begins when starlight passes through the atmosphere of an exoplanet. As this light travels through the planet's gaseous envelope, certain wavelengths are absorbed by the molecules present there. When this filtered light eventually reaches Webb's sensitive instruments, it contains dark lines or gaps at specific wavelengths, absorption features that reveal which molecules the light encountered on its journey. Each molecule creates a distinctive pattern of these absorption lines, allowing scientists to identify substances like water vapour, methane, carbon dioxide, or even potential biosignatures that might indicate the presence of life. Webb's exceptional capabilities for atmospheric analysis come primarily from two of its specialised instruments, the Near-Infrared Spectrograph, NIR-SPEC, and the Mid-Infrared Instrument, MIRI. NIR-SPEC is designed to analyse light in the near-infrared spectrum, which is particularly useful for studying cooler objects and detecting molecules like water and carbon dioxide. MIRI extends Webb's vision further into the mid-infrared range, allowing it to detect different molecular species and to study the thermal properties of exoplanet atmospheres. Together, these instruments provide complementary data that creates a more complete picture of an exoplanet's atmospheric composition. The technique most commonly used for exoplanet spectroscopy is called transit spectroscopy. When an exoplanet passes directly between its star and our telescope, an event called a transit, a small fraction of the starlight filters through the planet's atmosphere before reaching us. By comparing the spectrum of the star alone, observed when the planet is not transiting, with the spectrum obtained during transit, scientists can isolate the atmospheric contribution. This differential approach allows them to detect atmospheric components even when the planet itself is too faint to observe directly. What makes Webb particularly revolutionary for spectroscopy is its unprecedented sensitivity and spectral resolution. Previous telescopes could detect only the most abundant gases in the atmospheres of the largest exoplanets, mainly hot Jupiter-like worlds. Webb, however, can analyse the atmospheres of much smaller and cooler planets, including those that might be more similar to Earth. This capability represents a quantum leap in our search for potentially habitable worlds. The sensitivity required for this work is truly staggering. When a planet transits its star, typically less than 1% of the star's light is blocked by the planet itself. The atmospheric signature represents an even tinier fraction of that light, often just parts per million. Detecting such minute signals requires not only Webb's large collecting area and sophisticated instruments, but also advanced data processing techniques that can extract meaningful information from what appears to be noise. Spectroscopy doesn't just reveal which molecules are present, it can also provide crucial information about their abundance, distribution, and even the physical conditions in different layers of an atmosphere. By analysing how absorption features change across different wavelengths, scientists can construct vertical profiles of temperature and pressure within an exoplanet's atmosphere. This three-dimensional understanding helps reveal atmospheric dynamics like winds, circulation patterns, and even potential cloud formation. The power of spectroscopic analysis extends to detecting potential signs of life, known as biosignatures. On Earth, certain gases like oxygen and methane exist in our atmosphere at levels that would be difficult to maintain without biological processes. Finding similar chemical disequilibrium on an exoplanet, such as the simultaneous presence of both oxygen and methane, which typically react with each other, could suggest the presence of life. Webb's spectroscopic capabilities make it the first telescope potentially capable of detecting such biosignatures on planets around nearby stars. Another fascinating application of Webb's spectroscopic prowess is studying atmospheric escape. Many exoplanets, particularly those close to their stars, experience such intense radiation that their atmospheres are literally blown away into space. By analysing the extended envelope of gas surrounding such planets during transit, scientists can determine which elements are escaping and at what rate. This information provides crucial insights into atmospheric evolution and helps explain why some planets maintain substantial atmospheres while others become barren. The technical challenges involved in spectroscopic analysis of exoplanet atmospheres cannot be overstated. Scientists must account for contaminating signals from the host star, interstellar dust, and even our own solar system. They must develop sophisticated models that accurately represent how different molecules absorb light under the extreme temperature and pressure conditions found on alien worlds. And they must carefully distinguish true atmospheric features from instrumental artifacts or statistical flukes. Despite these challenges, Webb's spectroscopic capabilities are already yielding groundbreaking results. Early observations have detected water vapor in exoplanet atmospheres with unprecedented clarity and have begun to characterize the atmospheric compositions of potentially habitable worlds. These findings represent just the beginning of what promises to be a golden age of exoplanet characterization. The implications of these spectroscopic investigations extend far beyond simply cataloguing the chemical makeup of distant worlds. By comparing the atmospheres of many different exoplanets, scientists can begin to understand how planetary atmospheres form and evolve. They can identify patterns that reveal the influence of factors like planetary mass, orbital distance, stellar type, and system age. This comparative planetology provides crucial context for understanding our own solar system and Earth's place within it. Perhaps most profoundly, spectroscopy gives us the ability to search for environments potentially suitable for life as we know it. By identifying worlds with atmospheres containing water vapor, With temperatures allowing liquid water, and with protective features like ozone layers, we come closer to answering one of humanity's most fundamental questions: are we alone in the universe? While spectroscopy provides us the tools to analyse distant atmospheres, understanding what makes a planet potentially habitable requires us to explore the concept of the habitable zone, a framework that has evolved significantly in recent years thanks to observations from telescopes like the James Webb. The habitable zone, often informally called the Goldilocks zone, traditionally refers to the region around a star where temperatures would allow liquid water to exist on a planet's surface. This concept has been a cornerstone in our search for potentially life-supporting worlds since the 1990s. The classic definition is deceptively simple: not too close to the star where water would boil away, and not too far where it would freeze permanently. For a Sun-like star, this zone typically extends roughly from 95 million to 160 million kilometres, a relatively narrow band in astronomical terms. However, the James Webb Space Telescope is rapidly transforming our understanding of this concept, revealing that habitability involves far more complex factors than merely a planet's distance from its host star. The traditional model assumed Earth-like conditions, a rocky planet with a similar atmosphere and comparable internal heating. But Webb's observations are showing us a much more diverse universe of planetary environments where the rules might work quite differently. One major evolution in our understanding involves the role of atmospheric composition. A planet's atmosphere fundamentally changes how it processes stellar energy. A thicker atmosphere with more greenhouse gases can trap heat efficiently, potentially making a world in the outer edges of the traditional habitable zone quite warm. Conversely, a planet with a thin atmosphere or high reflectivity might remain frozen, despite sitting well within the classical habitable zone. Webb's ability to analyse atmospheric components is revealing just how dramatically these factors can expand or contract the regions where liquid water might exist. Planetary scientists now discuss effective habitable zones that account for these atmospheric variations. For instance, some research suggests that hydrogen-rich atmospheres, which are excellent at trapping heat, could extend the outer edge of the habitable zone by as much as 60%. This means that planets previously considered too cold for life might actually maintain liquid water under the right atmospheric conditions. Another significant evolution concerns the habitability of planets around different types of stars. Red dwarf stars, which are smaller and cooler than our Sun, have habitable zones much closer to the star itself. Initially, this proximity raised concerns about tidal locking, where one side of the planet perpetually faces the star, potentially creating a scorching day side and a frozen night side. However, atmospheric modelling based on Webb's observations suggests that efficient heat distribution through air and ocean currents could maintain habitable conditions even on tidally locked worlds. This finding dramatically increases the number of potentially habitable planets, as red dwarfs are the most common stars in our galaxy. The James Webb Space Telescope is also challenging our assumptions about habitability by revealing the potential for life in environments previously considered hostile. Some exoplanets orbit in eccentric ellipses rather than nearly circular paths like Earth's. Traditional models suggested such worlds would experience extreme seasonal temperature swings, making sustained habitability unlikely. Yet recent observations and models indicate that sufficient atmospheric density or large bodies of water could buffer these temperature variations, keeping conditions relatively stable despite a planet's eccentric orbit. Perhaps most intriguingly, Webb's capabilities are expanding our concept of habitability to include environments entirely unlike Earth's surface. Scientists now seriously consider the potential habitability of subsurface oceans on icy worlds, environments protected from harsh surface conditions by thick layers of ice. Evidence from our own solar system suggests such oceans exist beneath the surfaces of several moons, including Jupiter's Europa and Saturn's Enceladus. Webb can analyse the trace atmospheric components vented from these subsurface oceans, potentially revealing their chemical composition and habitability. The traditional habitable zone concept also failed to account for a star's evolution over time. Young stars emit more intense radiation than mature ones, meaning the habitable zone migrates outward as a star ages. A planet that forms in the habitable zone might not remain there throughout its history. Webb's ability to observe systems at different evolutionary stages is helping scientists understand how habitability can change over billions of years, introducing a crucial temporal dimension to our models. Magnetic fields represent another factor reshaping our understanding of habitable zones. A strong planetary magnetic field generated by a molten core shields a planet's atmosphere from stellar radiation that would otherwise strip away vital gases, including water vapour. Webb cannot directly observe magnetic fields, but by studying atmospheric composition and loss rates, it can help determine whether a planet likely possesses this crucial protective feature. The concept of habitable zones is also expanding beyond single stars. Many star systems in our galaxy are binaries or even triple star systems. Traditionally, these were considered less promising for habitability due to complex orbital dynamics and radiation environments. However, Webb's observations are showing that planets can maintain stable orbits and atmospheres even in these challenging settings, potentially expanding the cosmic real estate suitable for life. Even the definition of habitability itself is evolving. Rather than the simplistic habitable-uninhabitable binary, scientists now discuss a spectrum of habitability potential. Some worlds might support extremophile-type organisms in limited regions, while others could maintain Earth-like conditions across their entire surfaces. Between these extremes lies a vast diversity of partially habitable worlds with unique environmental niches. Webb's atmospheric analysis helps place exoplanets along this spectrum, rather than making absolute judgments about their life-supporting potential. The evolution of the habitable zone concept teaches us an important lesson about the search for life. We must avoid being overly Earth-centric. Life on our planet represents just one possible expression of biology in a vast universe of chemical and environmental possibilities. By expanding our understanding of where life might exist, the James Webb Space Telescope is fundamentally changing not just how we search for habitable worlds, but how we define habitability itself. This expanded view of habitability naturally leads us to consider what specific atmospheric features might actually indicate the presence of life on these diverse worlds. As we refine our understanding of where life might exist, we must simultaneously develop our ability to recognize its signs from afar. The search for biosignatures, chemical fingerprints that could indicate the presence of life, represents one of the most exciting applications of the James Webb Space Telescope's capabilities. A biosignature is essentially any substance, group of substances, or phenomenon that provides scientific evidence of past or present life. In the context of exoplanet atmospheres, scientists are particularly interested in certain gases that, on Earth, are predominantly produced by living organisms. Oxygen is perhaps the most discussed potential biosignature. On Earth, molecular oxygen makes up about 21% of our atmosphere and is primarily generated through photosynthesis. Without constant replenishment by plants and algae, oxygen would react with rocks and other materials and disappear from our atmosphere within a few million years. This is why finding substantial amounts of atmospheric oxygen on an exoplanet would be intriguing. It suggests some process, potentially biological, is continuously producing it. However, oxygen alone isn't a definitive biosignature. Scientists have identified several non-biological processes that could generate oxygen, including photochemical reactions where ultraviolet light splits water molecules in the upper atmosphere. This is why the James Webb Space Telescope's ability to detect multiple atmospheric components simultaneously is so crucial. Finding oxygen alongside other gases like methane would be far more compelling evidence for life. Methane represents another key biosignature target. On Earth, living organisms, particularly certain bacteria, produce the vast majority of atmospheric methane. Like oxygen, methane is relatively short-lived in atmospheres because it reacts with other compounds. Finding substantial methane alongside oxygen would be particularly interesting because these gases normally react with each other quickly. Their coexistence suggests both are being continuously replenished, possibly by biological processes. The James Webb Space Telescope's infrared capabilities make it exceptionally well suited to detect methane, which absorbs strongly in the infrared portion of the spectrum. Early observations have already demonstrated Webb's abilities to detect methane in exoplanet atmospheres with unprecedented sensitivity, though distinguishing biological sources from geological ones remains challenging. Carbon dioxide, while produced by both biological and non-biological processes, also plays an important role in the biosignature hunt. Its presence helps scientists understand the overall atmospheric context and carbon cycle of an exoplanet. For instance, a planet with both substantial methane and carbon dioxide, but little carbon monoxide might suggest biological methane production rather than volcanic sources. which would typically release all three gases. More complex molecules could provide even stronger evidence for life. Certain organic compounds like dimethyl sulfide are almost exclusively produced by living organisms on Earth. While detecting such complex molecules pushes the limits of current technology, Webb's exceptional sensitivity gives astronomers their first real chance to search for these more definitive biosignatures. Nitrous oxide represents another promising biosignature that Webb might detect. On Earth, this gas is primarily produced by microbes in soils and oceans. Unlike oxygen or methane, scientists have identified few non-biological processes that generate significant amounts of nitrous oxide, potentially making it a more reliable indicator of life. Webb also has the potential to detect seasonal variations in atmospheric composition, another possible biosignature. On Earth, carbon dioxide levels fluctuate annually as plant growth cycles respond to the seasons. Similar cyclical changes in an exoplanet's atmospheric chemistry could suggest the presence of a biosphere responding to seasonal changes in temperature or precipitation. The search for biosignatures faces several significant challenges. Perhaps the most fundamental is avoiding false positives, non-biological processes that mimic biological signatures. For instance, a planet that has lost most of its ocean water to space through atmospheric escape could accumulate oxygen without any life present. This is why scientists have developed sophisticated models that account for a planet's evolutionary history, stellar environment, and geological activity. Another major challenge involves distinguishing a true biological signal from the noise of observational data. The atmospheric signature of an Earth-sized planet is incredibly faint compared to the glare of its host star. Even with Webb's remarkable sensitivity, detecting biosignatures requires pushing instruments to their absolute limits and often combining data from multiple observations to boost signal strength. The third challenge involves interpreting potential biosignatures in environments dramatically different from Earth. Life on other worlds might use biochemistry unlike anything we're familiar with, potentially producing atmospheric signatures we wouldn't immediately recognize as biological. Conversely, what we consider a strong biosignature in Earth-like conditions might have completely non-biological explanations in exotic environments. This is why context matters tremendously. Understanding a planet's overall atmospheric composition, its stellar environment, and its evolutionary history all help scientists interpret potential biosignatures appropriately. Despite these challenges, the search for biosignatures has advanced from theoretical speculation to practical observation thanks to Webb's capabilities. Early observations have already characterized the atmospheres of several potentially habitable worlds, though conclusive biosignatures remain elusive. Each new data point helps refine our models and observational techniques, gradually increasing our ability to distinguish biological from non-biological signatures. Perhaps the most exciting aspect of the biosignature hunt is its potential to identify not just the presence of life, but its nature and abundance. Different types of metabolisms produce different atmospheric effects. By analysing the precise mixture and concentrations of various gases, scientists might eventually determine whether a distant world hosts simple microbial life or complex ecosystems with diverse metabolic strategies. Such insights would revolutionize our understanding of how common different forms of life might be throughout the cosmos. The search for biosignatures brings our attention to specific types of potentially habitable worlds, and among the most fascinating candidates are water worlds, planets potentially covered entirely by deep oceans. While the James Webb Space Telescope continues its survey of distant atmospheres, it's uncovering evidence of planets that might be dominated by water to an extent that makes Earth, with its mix of continents and seas, seem relatively dry by comparison. Water worlds represent a planetary class quite unlike anything in our solar system. While Earth's surface is approximately 70% covered by oceans, these exoplanets might have no exposed land whatsoever, just a continuous global ocean extending across their entire surface. The James Webb Telescope has detected several promising candidates for such worlds, primarily through observations of their atmospheric water vapor content and overall density measurements that suggest a substantial portion of their mass consists of water. What makes these planets particularly interesting is their composition. Unlike Earth, where water represents just about 0.02% of our planet's total mass, water worlds might have water constituting anywhere from 10 to 50% of their total planetary mass. This abundance creates fundamentally different planetary structures than what we're familiar with. Rather than a relatively thin ocean sitting atop a rocky crust, these planets likely have water extending downward for hundreds or even thousands of kilometres. At such depths, the immense pressure creates exotic forms of water unlike anything we experience on Earth. Scientists believe these deep ocean layers might contain hot ice, water that remains solid despite high temperatures due to extreme pressure. Deeper still, there may be superionic water, where water molecules break apart and oxygen atoms form a crystal lattice, while hydrogen atoms flow freely like a liquid. These strange states of water would form distinct layers within the planet, creating a structure somewhat like a water-based version of Earth's core, mantle, and crust system. The atmospheres of water worlds also present unique characteristics that the James Webb Telescope is particularly well equipped to study. Their atmospheres would likely be dominated by water vapour, with potentially thick cloud layers composed of water droplets or ice crystals depending on the planet's temperature. Webb's infrared instruments can penetrate these cloud layers to some degree, allowing scientists to study the atmospheric composition in detail and confirm the water-rich nature of these worlds. The origins of water worlds raise intriguing questions about planetary formation. One theory suggests they might form beyond the snow line of their solar systems, the distance from the star where water freezes, accumulating massive amounts of ice during formation, and then migrate inward to warmer orbits where this ice melts. Alternatively, they might form from water-rich materials closer to their stars. The James Webb Telescope's observations of young solar systems and protoplanetary disks are helping clarify these formation pathways by revealing the distribution of water and other volatiles during planetary system formation. Life on water worlds would face very different evolutionary pressures than life on Earth. Without land, photosynthesis as we know it might be limited to the uppermost ocean layers. However, these planets might develop rich ecosystems around hydrothermal vents on their seafloors, similar to Earth's deep-sea vent communities that thrive without sunlight using chemosynthesis. The immense pressure of these deep global oceans might also create unique environmental niches with no equivalent on Earth, potentially fostering truly alien forms of life. The climate dynamics of water worlds would differ dramatically from Earth's. Without land masses to interrupt ocean currents, these planets might develop powerful planet-spanning current systems that efficiently distribute heat from their day sides to night sides. This could be especially important for water worlds orbiting red dwarf stars, which are likely to be tidally locked. Efficient heat distribution might prevent the freezing of their night sides, potentially maintaining liquid water across their entire surface despite receiving light from only one side. Despite their abundance of water, often considered a prerequisite for life, water worlds might actually be less hospitable than planets with a mix of land and sea. The immense depth of their oceans could create a barrier between the water surface and the rocky seafloor, potentially preventing the crucial cycling of minerals and nutrients that supports life on Earth. Without land masses, these worlds would also lack the weathering processes that help regulate carbon dioxide levels, potentially making their climates less stable over geological timescales. The James Webb Space Telescope's observations are helping resolve some of these questions by characterizing the atmospheres of several water world candidates. By measuring their atmospheric composition, temperature profiles, and cloud patterns, scientists are developing a better understanding of how these unique planets function. These observations are particularly valuable because our own solar system lacks examples of true water worlds, making exoplanet studies our only window into understanding this apparently common planetary type. As we continue to discover and characterize more of these ocean-dominated planets, we're developing a deeper appreciation for the astonishing diversity of worlds that exist beyond our solar system. Water worlds represent just one example of how planets can develop along evolutionary paths quite different from the terrestrial worlds we're most familiar with, highlighting the remarkable variety of environments that might exist throughout our galaxy. This diversity of planetary types leads us naturally to consider the most common classes of exoplanets discovered so far, super-Earths and mini-Neptunes. One of the most surprising revelations from exoplanet surveys has been that the most abundant planetary types in our galaxy appear to be those that have no direct equivalent in our own solar system. Super-Earths and mini-Neptunes occupy the size range between Earth and Neptune, with radii typically between 1.3 and 4 times that of Earth. This size range represents a significant gap in our solar system. We have the terrestrial planets, Mercury, Venus, Earth and Mars, all smaller than 1.3 Earth radii, and then nothing until we reach Neptune at about 4 Earth radii. Yet the James Webb Space Telescope and previous exoplanet surveys have revealed that planets in this missing size range are remarkably common around other stars. The distinction between super-Earths and mini-Neptunes isn't just about size, but also composition. Super-Earths are primarily rocky worlds, essentially scaled-up versions of Earth, with solid surfaces and relatively thin atmospheres. Mini-Neptunes, on the other hand, have substantial gaseous envelopes surrounding smaller rocky or icy cores. The dividing line between these categories occurs at approximately 1.7 times Earth's radius, though this boundary isn't absolute and depends on other factors like a planet's density and temperature. What makes these planet types particularly interesting is that they represent a critical transition zone in planetary formation. Somewhere between Earth size and Neptune size, planets seem to accumulate enough mass to hold on to significant amounts of hydrogen and helium from the protoplanetary disk during formation. Understanding exactly when and why this transition occurs is one of the major questions the James Webb Telescope is helping to address through its atmospheric observations. Super-Earths display remarkable diversity in their properties. Some appear to be essentially scaled-up versions of our own planet, with similar compositions dominated by silicate rocks and iron. Others might have exotic compositions unlike anything in our solar system. Carbon planets, potentially containing massive amounts of diamond, lava worlds, with molten surface oceans, or the water worlds discussed previously. Webb's infrared capabilities allow scientists to distinguish between these different types by analysing their atmospheric composition and thermal properties. Particularly intriguing are super-Earths located in their stars' habitable zones. These worlds have generated significant excitement because they might combine Earth-like conditions with greater mass, which offers certain advantages for habitability. Their stronger gravity would help retain thicker atmospheres, potentially providing better protection from stellar radiation and cosmic rays. Their larger size might also support more vigorous plate tectonics and longer-lasting internal heat, both considered potentially beneficial for maintaining habitable conditions over the long timescales needed for complex life to evolve. Mini-Neptunes present a different set of fascinating questions. Until recently, scientists generally assumed these planets would be uninhabitable due to their thick hydrogen-helium atmospheres and lack of solid surfaces. However, recent models suggest that some mini-Neptunes, particularly those receiving significant stellar radiation, might lose their primordial hydrogen over time. This atmospheric evolution could potentially transform a mini-Neptune into a super-Earth, moving it from the uninhabitable to potentially habitable category. Even more surprising, some research indicates that certain mini-Neptunes might be habitable, even without losing their gaseous envelopes. If temperatures and pressures at the boundary between the atmosphere and underlying magma ocean or water layer are suitable, liquid water could exist at this interface. Such environments would be completely unlike Earth's surface conditions, but might still support some form of life. The James Webb Space Telescope is revolutionizing our understanding of these common exoplanet types through detailed atmospheric characterization. By analyzing the composition and structure of their atmospheres, scientists can infer their formation history, current conditions, and potential habitability. Webb's sensitivity allows it to study the atmospheres of much smaller planets than was previously possible, bringing super-Earths, the most likely candidates for Earth-like conditions, into the realm of detailed study for the first time. One of the most significant questions Webb is helping to answer concerns the mysterious radius gap discovered in exoplanet statistics. Data shows a curious shortage of planets with radii around 1.8 times that of Earth, exactly at the transition between super-Earths and mini-Neptunes. This gap suggests that planets tend to form as either rocky super-Earths or gaseous mini-Neptunes, with few intermediate cases. By characterizing atmospheres on both sides of this divide, Webb is providing crucial insights into the processes that create this bimodal distribution. The prevalence of super-Earths and mini-Neptunes has profound implications for our understanding of planetary system formation. Their common occurrence suggests that the conditions leading to these planet types are the norm rather than the exception, making our own solar system's architecture somewhat unusual. This realization has prompted scientists to reconsider traditional models of planetary formation, which were naturally based on the only example we had, our own system. The interior structures of these planets remain largely theoretical, constrained primarily by their measured masses and radii. Super-Earths likely have differentiated interiors similar to Earth but scaled up. An iron-rich core surrounded by a silicate mantle and potentially a thin crust. Mini-Neptunes probably have rocky or icy cores surrounded by thick envelopes of hydrogen, helium and water. Webb's atmospheric observations provide indirect clues about these internal structures by revealing which elements have made their way from the interior to the atmosphere through geological processes like volcanism. The discovery that these intermediate-sized planets are the most common types in our galaxy has transformed exoplanet science. When we consider the population of planets as a whole, Earth appears somewhat small compared to the typical rocky world. This perspective shift reminds us that our concepts of what constitutes a normal planet continue to evolve as we gather more data. With each new super-Earth or mini-Neptune characterized by the James Webb Space Telescope, we gain a clearer picture of the incredible diversity of worlds that populate our galaxy and the many forms that potentially habitable environments might take. While super-Earths and mini-Neptunes represent the most common exoplanets in our galaxy, the James Webb Space Telescope is also providing unprecedented insights into more extreme worlds, particularly the fascinating and bizarre category known as hot Jupiters. These exotic giants were actually among the first exoplanets ever discovered, not because they're especially common, but because their distinctive properties made them easier to detect with earlier technology. Hot Jupiters are gas giant planets similar in size and composition to our own Jupiter, but orbiting astonishingly close to their host stars, typically at distances less than 1/10 of Mercury's orbit around our Sun. This proximity creates truly extreme conditions unlike anything in our solar system. Surface temperatures on these worlds can exceed 2000 degrees Celsius, hot enough to melt steel and even some rocks. At these temperatures, the very chemistry of their atmospheres becomes alien and exotic compared to the cooler gas giants we're familiar with. What makes hot Jupiters particularly valuable targets for the James Webb Space Telescope is the combination of their size and temperature. Their large diameters mean they block significant amounts of starlight during transit, creating stronger atmospheric signals. Meanwhile, their high temperatures cause them to glow brightly in infrared wavelengths, precisely where Webb's instruments are most sensitive. This fortunate convergence of properties makes hot Jupiter atmospheres among the most accessible for detailed study, serving as cosmic laboratories for understanding atmospheric physics under extreme conditions. The James Webb Telescope's observations are revealing that hot Jupiter atmospheres exhibit bizarre weather patterns driven by their extreme thermal conditions. Unlike Jupiter in our solar system, where temperature differences between the equator and poles drive weather patterns, hot Jupiters are dominated by the temperature contrast between their permanent day and night sides. These planets are typically tidally locked to their stars, meaning one hemisphere perpetually faces the scorching star while the other remains in eternal night. This stark division creates temperature differences of up to 1000 degrees between the day and night sides, generating ferocious winds that can reach speeds of thousands of kilometers per hour, far stronger than the most violent hurricanes on Earth. These winds create a displacement between the hottest point on the planet and the point directly facing the star, a phenomenon Webb can detect by measuring how the infrared emission changes as the planet orbits. The telescope's precision allows scientists to essentially map weather patterns on these distant worlds. Perhaps the most exotic feature of hot Jupiter atmospheres is their unusual cloud composition. At the blistering temperatures these planets experience, substances that would be solid rock on Earth can exist as vapor in the atmosphere. As this vapor moves to cooler regions or higher altitudes, it can condense to form clouds, but not water clouds like on Earth. Instead, Webb is detecting evidence of clouds made of vaporized silicates similar to sand, iron, titanium oxide, aluminum oxide, the material of rubies and sapphires, and other exotic materials. These unusual clouds don't just make for interesting weather forecasts, they fundamentally alter how the planet's atmosphere processes radiation from its star. Some of these cloud types are highly reflective, bouncing back significant amounts of starlight, while others absorb certain wavelengths of light and re-emit them as heat. Webb's ability to analyze exactly how light interacts with these atmospheres at different wavelengths allows scientists to determine which cloud compositions are present and how they affect the planet's overall energy balance. The intense radiation these planets receive from their nearby stars also triggers complex photochemical reactions in their upper atmospheres. Webb has detected evidence of molecules being broken apart and recombined into new compounds through these processes. Some hot Jupiters that show signatures of unusual carbon and nitrogen chemistry that wouldn't occur under less extreme conditions. These reactions sometimes produce haze layers of tiny particles suspended in the atmosphere, similar to smog on Earth but composed of exotic compounds like hydrocarbons and nitriles. One particularly interesting, question, the James Webb Telescope is addressing concerns why some hot Jupiters appear to have relatively clear atmospheres, while others are shrouded in thick hazes that obscure our view of deeper atmospheric layers. Early results suggest that factors like the planet's specific temperature, gravity, and the intensity and spectrum of radiation from its host star all play important roles in determining atmospheric clarity. Understanding these relationships helps scientists develop better models of atmospheric behaviour that can be applied to a wide range of planets. Another fascinating aspect of hot Jupiter atmospheres that Webb is investigating involves atmospheric escape, the process by which gases are lost to space. The intense heat and radiation these planets experience can energize atoms and molecules in the upper atmosphere enough for them to escape the planet's gravitational pull. Webb has observed extended clouds of hydrogen, helium, and even heavier elements surrounding some hot Jupiters, creating comet-like tails as material streams away from the planet. Measuring the rate and composition of this escaping material helps scientists understand how planetary atmospheres evolve over time. The composition of hot Jupiter atmospheres also provides important clues about how and where these planets formed. Most astronomers believe these giants must have formed much farther from their stars, where conditions were cool enough for gases and ices to accumulate, and then migrated inward through complex gravitational interactions. Webb's measurements of elements like carbon, oxygen, and various metals in their atmospheres can test this theory by revealing whether their chemical makeup matches what we would expect from formation in the outer regions of a solar system. Despite their inhospitable conditions, the study of hot Jupiter atmospheres has important connections to the search for habitable worlds. The extreme environments they present allow scientists to test atmospheric models under conditions that challenge their fundamental assumptions. When these same models are applied to potentially habitable planets, having verified them under extreme conditions increases our confidence in their predictions. Additionally, understanding how stellar radiation affects atmospheric chemistry and stability helps us better evaluate the habitability of planets around various types of stars. The knowledge gained from Webb's observations of hot Jupiters is already informing the next generation of exoplanet characterization missions and improving our models of atmospheric physics across a wide range of conditions. Each new hot Jupiter studied adds another data point to our understanding of these extreme worlds, gradually building a comprehensive picture of how atmospheres behave across the full spectrum of planetary environments. From the hellish conditions of hot Jupiters, we turn to a planetary system that offers a very different kind of natural laboratory for atmospheric studies, the remarkable TRAPPIST-1 system. Discovered in 2016 and quickly becoming one of the most intensely studied exoplanetary systems, TRAPPIST-1 presents an unprecedented opportunity to compare the atmospheres of multiple Earth-sized worlds within a single compact system. Located about 40 light-years from Earth, the TRAPPIST-1 system consists of 7 rocky planets orbiting an ultra-cool dwarf star that's just 8% the mass of our Sun. What makes this system extraordinary from a comparative planetology perspective is the remarkable similarity in size among these worlds. All 7 planets have diameters comparable to Earth, differing by no more than 15%. This size consistency provides a controlled variable, allowing scientists to isolate how other factors influence atmospheric development when planet size remains relatively constant. The compact nature of the TRAPPIST-1 system is difficult to overstate. All 7 planets orbit closer to their star than Mercury orbits our Sun, yet because TRAPPIST-1 is so much cooler than the Sun, 3 of these worlds still fall within the traditional habitable zone. The entire system would fit comfortably within Mercury's orbit, with the outermost planet completing an orbit in just 19 Earth days. This compactness creates unique opportunities for the James Webb Space Telescope, as it can efficiently observe multiple planets within a relatively short time frame, sometimes even catching several transits in a single observation session. What makes TRAPPIST-1 truly invaluable as a natural laboratory is that these planets likely formed from the same protoplanetary disk, meaning they started with very similar inventories of elements and compounds. This shared origin allows scientists to isolate how a planet's distance from its star influences atmospheric evolution when initial composition is held relatively constant, a comparative experiment that would be impossible to arrange deliberately and that doesn't exist elsewhere in our observational catalogue. The James Webb Space Telescope has made TRAPPIST-1 a priority target precisely because of this scientific value. Webb's exceptional sensitivity to infrared light makes it particularly well suited for studying this system as cool dwarf stars like TRAPPIST-1 emit most of their radiation in the infrared portion of the spectrum. This alignment between the star's emission and Webb's detection capabilities maximizes the strength of atmospheric signals during transits and eclipses. One of the most pressing questions Webb is addressing concerns which, if any, of the TRAPPIST-1 planets have retained substantial atmospheres. This question has significant implications for habitability, as atmospheres are crucial for moderating surface temperatures and protecting against radiation. Early observations have yielded intriguing but complex results. Several planets show evidence of atmospheres, but their compositions appear to differ significantly despite their similar sizes and formation conditions. These differences highlight how a planet's specific distance from its star can dramatically alter its evolutionary trajectory. The 3 planets in TRAPPIST-1's habitable zone, designated E, F, and G, have attracted particular attention. Webb's spectroscopic observations are searching for water vapour and other volatiles in their atmospheres that might indicate their potential to host liquid water. Preliminary data suggests at least one of these worlds may have retained water vapour in its atmosphere, though confirming these tentative detections requires additional observations and analysis. The presence or absence of water in these atmospheres provides crucial insights into the delivery and retention of volatiles on rocky planets, processes fundamental to the development of habitable conditions. A significant challenge in studying the TRAPPIST-1 planets stems from the nature of their host star. Like many red dwarf stars, TRAPPIST-1 is quite active, experiencing frequent flares that bathe its planets in bursts of high-energy radiation. Webb's observations are helping determine how these stellar eruptions affect planetary atmospheres over time. The telescope can detect signatures of atmospheric escape following particularly intense flares, measuring how quickly gases are stripped away from different planets in the system. This data helps answer a crucial question in astrobiology: whether planets around active stars can maintain atmospheres suitable for life over billions of years. The compact configuration of the TRAPPIST-1 system also creates interesting gravitational interactions between the planets. All 7 worlds are in orbital resonance with each other, meaning their orbital periods form simple integer ratios. These resonances cause the planets to regularly align in patterns that slightly accelerate or decelerate each other through gravitational tugs. Webb's precise measurements of transit timing variations caused by these interactions allow scientists to calculate each planet's mass with remarkable accuracy, which in turn helps constrain their internal compositions. Understanding whether a planet is primarily rock, has a substantial water component, or contains significant amounts of iron provides essential context for interpreting atmospheric observations. Another fascinating aspect of the TRAPPIST-1 system that Webb is investigating involves potential atmospheric exchange between neighbouring planets. Given their close proximity, material ejected from one planet's atmosphere, particularly during intense torque flaring events, could potentially be captured by another planet's gravity. This atmospheric sharing, if detected, would represent a previously unconsidered aspect of planetary evolution in compact systems and might help explain unexpected compositional similarities or differences between otherwise distinct worlds. Perhaps the most valuable aspect of studying the TRAPPIST-1 system is the opportunity to compare atmospheric conditions across multiple habitable zone planets within the same system. Earth represents our only example of a habitable world, making it difficult to distinguish which of its properties are necessary for habitability and which are merely contingent results of its specific evolutionary history. By comparing multiple potentially habitable worlds with similar initial conditions but different evolutionary paths, scientists can begin to identify the truly essential ingredients for planetary habitability. The TRAPPIST-1 system also holds special significance in our search for life beyond Earth. Red dwarf stars like TRAPPIST-1 are the most common type of star in our galaxy, comprising about 70% of all stars. If habitable conditions can exist on planets orbiting such stars, the potential abodes for life would be vastly more numerous than if habitability were restricted to Sun-like stars. Webb's detailed characterization of this system therefore has implications that extend far beyond these 7 specific planets. It informs our understanding of the habitability potential for the majority of planetary systems in our galaxy. While the TRAPPIST-1 system offers an exceptional laboratory for comparative planetary studies, it also highlights one of the greatest technical challenges in exoplanet research: detecting and characterizing atmospheres around rocky planets. This challenge represents the frontier of what's technically possible with current technology, pushing the James Webb Space Telescope to its absolute limits. Detecting atmospheres around rocky Earth-sized planets is exponentially more difficult than studying the atmospheres of larger worlds like hot Jupiters or mini-Neptunes. The fundamental challenge comes down to scale. Rocky planets are simply much smaller than their gaseous counterparts. When a planet transits its star, the amount of starlight that filters through its atmosphere is proportional to the atmosphere's physical size. For a Jupiter-sized planet, this atmospheric ring represents a substantial area that produces a relatively strong signal. For an Earth-sized planet, this same ring is dramatically smaller, producing an atmospheric signal that might be 100 times weaker. This signal weakness is compounded by the fact that rocky planets are expected to have much thinner atmospheres than gas giants. While hot Jupiters have atmospheric envelopes extending thousands of kilometers above their surfaces, a rocky planet's atmosphere might only extend a few dozen kilometers up. This makes the effective area for atmospheric transmission spectroscopy dramatically smaller, further reducing the already faint signal. The James Webb Space Telescope tackles this challenge through several approaches. First, its unprecedented collecting area, with a primary mirror over 6 times the area of Hubble's, allows it to gather far more light, improving signal-to-noise ratios for all observations. Second, its exceptional thermal stability, achieved by operating at the L2 Lagrange point with sophisticated temperature control system, reduces instrumental noise that could otherwise drown out the faint atmospheric signals. Third, Webb's specialized instruments like NARSpec and MIRI are optimized for precisely the types of measurements needed to detect these subtle atmospheric imprints. Even with these advantages, detecting atmospheres on rocky planets requires extraordinary observational strategies. Scientists often need to combine data from multiple transits of the same planet, sometimes 10 or more, to gradually build up a strong enough signal to confirm the presence of an atmosphere. This process can require dozens of hours of precious telescope time for a single planet, highlighting why only the most promising candidates receive such intensive scrutiny. The challenge is particularly acute for planets orbiting Sun-like stars. These stars are relatively large and bright compared to red dwarfs, like TRAPPIST-1, creating an even more unfavourable planet-to-star size ratio that further weakens the atmospheric signal. This is one reason why much of Webb's rocky planet atmosphere work focuses on worlds orbiting smaller stars, despite the potential habitability challenges these systems face. Another significant obstacle involves disentangling the planet's atmospheric signal from the intrinsic variability of the host star itself. Stars aren't perfect, unchanging light sources. They have spots, flares, and other features that cause their brightness to fluctuate slightly. For gas giants, these stellar variations are usually much smaller than the atmospheric signal. For rocky planets, stellar variability can be similar in magnitude to the atmospheric features scientists are trying to detect, and creating a complex statistical problem of separating these entangled signals. The search for atmospheres around rocky planets must also contend with the possibility that many of these worlds simply don't have substantial atmospheres at all. Recent research suggests that atmospheric loss might be common, particularly for planets orbiting active stars. The James Webb Telescope is not only trying to detect atmospheres, but also to constrain their absence when they don't exist. Information that's equally valuable for understanding the conditions necessary for atmosphere retention. Perhaps the most formidable technical challenge involves atmospheric composition determination. Detecting the mere presence of an atmosphere is difficult enough, but identifying specific molecules within that atmosphere requires isolating the absorption features of individual gases from an already faint signal. This is where Webb's spectroscopic capabilities are truly revolutionary. Its ability to spread light into finely detailed spectra allows it to potentially identify specific molecular signatures that previous telescopes could never resolve. The search for atmospheres around rocky planets benefits greatly from advances in data processing techniques. Sophisticated statistical methods like Bayesian inference and machine learning algorithms are increasingly important for extracting the maximum amount of information from Webb's observations. These computational approaches can detect patterns in the data too subtle for traditional analysis, helping overcome the fundamental signal limitations. Despite these formidable challenges, the James Webb Space Telescope has already achieved early successes in this domain. It has provided the first definitive evidence for carbon dioxide in the atmosphere of a Neptune-sized planet and made tentative detections of atmospheres around several super-Earths. While confirming atmospheres around truly Earth-sized planets remains the most challenging frontier, each observation brings us closer to this goal by refining techniques and building our understanding of atmospheric properties across the size spectrum. The high stakes of this challenge explain why it commands such attention. Detecting atmospheres on rocky planets represents a crucial step toward identifying potentially habitable worlds. An atmosphere is a prerequisite for surface liquid water and provides protection from radiation, making atmospheric characterization essential for habitability assessment. Each successful detection also helps answer fundamental questions about how common atmospheres are on rocky planets and what factors determine their presence or absence. This work also highlights the extraordinary technical achievement that the James Webb Space Telescope represents. The ability to detect molecules in the atmospheres of small rocky planets orbiting stars trillions of miles away would have seemed like science fiction just decades ago. That we can now even attempt such measurements, and in some cases succeed, demonstrates the remarkable progress of both our technological capabilities and our understanding of exoplanet atmospheres. The incredible difficulty of detecting atmospheres on rocky planets naturally leads us to examine exactly how the James Webb Space Telescope accomplishes this feat. The primary method Webb uses to study exoplanet atmospheres is transit spectroscopy, a clever technique that takes advantage of rare geometric alignments when planets pass directly between their stars and our telescope. When a planet transits its star, most of the starlight is blocked by the solid body of the planet itself. However, a small but crucial fraction of light passes through the thin ring of atmosphere surrounding the planet's disk. As this light travels through the atmosphere, certain wavelengths are absorbed by the various gases present, while others pass through relatively unaffected. By precisely measuring which wavelengths are absorbed and to what degree, scientists can determine both the presence of an atmosphere and its chemical composition. The actual process of a transit observation with Webb follows a carefully choreographed sequence. Well before the transit begins, the telescope locks onto the target star and begins collecting baseline data. This pre-transit observation is crucial because it establishes the normal, unfiltered spectrum of the star alone. Then, as the planet moves into the transit position, Webb continues collecting data continuously through the entire event, which might last anywhere from a few hours for close orbiting planets to over a day for planets in wider orbits. After the transit concludes, Webb typically continues observing for some additional time to collect post-transit baseline data. This three-phase observation, before, during, and after transit, allows scientists to isolate the tiny atmospheric contribution by comparing the in-transit spectrum with the out-of-transit baseline. The difference between these spectra, usually just fractions of a percent in intensity, contains the atmospheric signature. The technical precision required for these observations is astonishing. For Earth-sized planets, the atmospheric signal might alter the observed starlight by just 10 parts per million or less. Detecting such minute changes requires extraordinary instrumental stability and sophisticated data processing to remove various sources of noise. Webb achieves this precision through multiple design elements, including its thermal stability, its precision pointing system, and its highly sensitive detectors that can count individual photons of light. Transit spectroscopy works most effectively at wavelengths where the planet's atmosphere is relatively opaque, but the star remains bright. The ideal wavelength ranges differ depending on which atmospheric components scientists are targeting. Water vapour, for example, has strong absorption features in the near-infrared, while carbon dioxide and methane have distinctive features at slightly longer wavelengths. Webb's instruments cover a broad infrared range specifically to capture these various molecular signatures. While transit observations provide information about the composition of the atmosphere, they have a specific limitation. They primarily probe the atmosphere at the terminator, the boundary between the planet's day and night sides. This region might not be representative of the entire atmosphere, particularly for tidally locked planets where temperature differences between day and night sides can be extreme. To develop a more complete picture, astronomers complement transit observations with a second technique called secondary eclipse spectroscopy. Secondary eclipses occur when a planet passes behind its star from our perspective. Just before disappearance, we see the planet's day side fully illuminated. By comparing the combined light of the star plus planet system just before eclipse with the light of the star alone during eclipse, astronomers can isolate the planet's emission spectrum. This approach provides information about the temperature structure of the atmosphere and can reveal different compositional information than transit observations. For some close-orbiting planets, Webb can even observe how the infrared emission changes as different portions of the planet rotate in and out of view. This technique, called phase curve analysis, allows scientists to map temperature variations across the planet's surface and measure how efficiently heat is redistributed from the day side to the night side, crucial information for understanding atmospheric circulation. The James Webb Telescope can also study atmospheres through direct imaging for a small subset of planets, typically young, massive planets orbiting far from their stars. By blocking the star's light with the specialized coronagraphic instruments, Webb can sometimes directly capture the faint glow of a planet. This approach provides access to a different class of planets than transit methods, which are biased toward close-orbiting worlds. For most rocky planets, however, transit spectroscopy remains the primary technique. The process requires extraordinarily precise knowledge of when the transits will occur, often predicted based on previous observations from telescopes like TESS, Transiting Exoplanet Survey Satellite, or ground-based facilities. Webb's observing schedule is carefully optimized to capture these transits, which represent rare and valuable opportunities to probe planetary atmospheres. The interpretation of transit spectroscopy data is as challenging as its collection. Raw data must undergo extensive processing to remove systematic effects from both the instrument and the observation process. Scientists then compare the processed spectra against theoretical models of various possible atmospheric compositions, using statistical techniques to determine which compositions best match the observed data. This process often involves testing thousands of potential atmospheric models against the observations to find the best matches. The power of Webb's transit spectroscopy approach is clearly demonstrated by its early results. In observations of the hot Saturn-sized planet WASP-39b, Webb detected multiple molecules including water vapor, carbon dioxide, carbon monoxide, and sulfur dioxide, the latter being the first definitive detection of this molecule in any exoplanet atmosphere. These results showcase how the transit spectroscopy can reveal not just the presence of an atmosphere, but its detailed chemical inventory. As the mission continues, Webb's transit observations will gradually build a comprehensive catalogue of exoplanet atmospheres spanning a wide range of planetary sizes, temperatures, and stellar environments. Each new observation refines our understanding of how atmospheres form, evolve, and vary across different types of worlds, helping answer fundamental questions about the prevalence and diversity of atmospheres throughout our galaxy. Transit spectroscopy gives us a powerful window into the composition of distant atmospheres, but it also reveals a dramatic process occurring on many exoplanets: atmospheric escape. As the James Webb Space Telescope examines planets closely orbiting their stars, it frequently observes atmospheres that are literally blowing away into space, creating comet-like tails that stream behind planets as they orbit. Atmospheric escape occurs when energy from the host star heats the uppermost layers of a planet's atmosphere, energizing the gas molecules to the point where they can reach escape velocity and permanently leave the planet's gravitational influence. This process is happening even to Earth. We lose approximately 90 tons of hydrogen and helium to space every day. But for many exoplanets, particularly those close to their stars, this loss happens at dramatically accelerated rates. The most common form of atmospheric escape detected by Webb is known as thermal escape, or Jeans escape, where the natural thermal motion of gas particles occasionally sends some molecules moving fast enough to escape gravity. This process preferentially affects lighter elements like hydrogen and helium, which require less energy to reach escape velocity. For many close-orbiting exoplanets, the intense stellar heating can raise the temperature of the upper atmosphere to over 10,000 degrees Celsius, making thermal escape extremely efficient. An even more dramatic form of atmospheric loss observed by Webb is hydrodynamic escape, sometimes called atmospheric blow-off. This occurs when stellar radiation is so intense that it heats the upper atmosphere to such extreme temperatures that the atmosphere begins to expand dramatically, creating a pressure gradient that drives a massive outflow of gas. Under these conditions, the escaping hydrogen can drag heavier elements along with it, allowing even relatively massive molecules to escape that would normally be gravitationally bound. The James Webb Space Telescope is ideally suited to observe these atmospheric escape processes. During transit observations, Webb can detect an extended cloud of gas surrounding and trailing the planet. appearing as excess absorption before and after the main transit. The telescope's infrared capabilities are particularly effective at detecting escaping hydrogen, which produces distinctive absorption features in the infrared spectrum. For some planets experiencing extreme atmospheric loss, Webb can even create rough maps of the escaping gas cloud, showing how it is shaped by the interactions with the stellar wind. Planets orbiting red dwarf stars are particularly susceptible to atmospheric loss, despite these stars having lower overall luminosity than Sun-like stars. The issue is that red dwarfs emit a much higher proportion of their energy as high-energy ultraviolet and X-ray radiation, especially during their frequent flares. This energetic radiation is particularly effective at heating upper atmospheres and driving escape. Webb's observations of several planets around red dwarf stars are showing evidence of significant atmospheric loss, raising concerns about the long-term habitability of planets around these common stellar hosts. Magnetic fields play a crucial role in protecting atmospheres from escape, acting as shields against the stellar wind and creating a barrier that prevents some forms of atmospheric loss. Earth's magnetic field, generated by its molten core, dramatically reduces our atmospheric loss rate. The James Webb Telescope cannot directly observe magnetic fields, but it can indirectly infer their presence or absence by measuring atmospheric loss rates. Planets showing unexpectedly low levels of escape despite close proximity to their stars may be protected by strong magnetic fields, while those with excessive loss might lack this crucial protection. The implications of atmospheric escape extend far beyond the current state of these planets. This process shapes planetary evolution over billions of years. Many planets that formed with thick hydrogen-helium envelopes may have lost these primordial atmospheres entirely, transforming from mini-Neptunes to rocky super-Earths. Webb's ability to detect the rate of current atmospheric loss allows scientists to model this evolutionary history, estimating how much atmosphere a planet might have lost since its formation and predicting its future development. One particularly intriguing question Webb is investigating is whether atmospheric escape can render initially uninhabitable planets potentially habitable over time. Some planets may form with massive hydrogen-dominated atmospheres that create surface pressures far too high for liquid water. As these atmospheres gradually escape to space, surface conditions might eventually moderate into a habitable range. Conversely, initially habitable planets might lose their atmospheres entirely, highlighting how atmospheric evolution can both create and destroy habitable conditions. The composition of escaping gas also reveals important information about a planet's atmosphere. Webb can determine which elements are preferentially lost to space, helping scientists understand both the current atmospheric makeup and how it has changed over time. For instance, if a planet shows evidence of losing primarily hydrogen but retaining heavier gases like oxygen, this suggests the atmosphere is becoming progressively enriched in these heavier components, a process that has significant implications for atmospheric chemistry and potential habitability. Some of the most extreme examples of atmospheric escape observed by Webb occur on hot rocky planets so close to their stars that their surface materials vaporize, creating tenuous atmospheres of rock vapor that continuously stream away to space. These disintegrating planets represent the end stages of atmospheric loss, where not only the original atmosphere but even the planetary surface itself is being lost to space. Studying these extreme cases helps scientists understand the ultimate fate of planets that migrate too close to their stars. The story of atmospheric escape links directly to another crucial aspect of planetary atmospheres, their origins. While some planets manage to retain portions of their primordial atmospheres, captured during formation, many rocky worlds have what scientists call secondary atmospheres, gaseous envelopes created not during planet formation, but through subsequent processes like volcanic eruptions and comet impacts. Secondary atmospheres represent a fundamentally different type of planetary envelope than the primary atmospheres of gas giants like Jupiter and Saturn. Primary atmospheres consist mainly of hydrogen and helium captured directly from the protoplanetary disk during formation. These light gases are the most abundant elements in the universe, but are easily lost by smaller planets due to the atmospheric escape processes we just discussed. Secondary atmospheres, in contrast, form after this initial atmospheric loss and are typically dominated by heavier gases that are more resistant to escape. Volcanic activity represents the most significant source of secondary atmospheres on rocky planets. As a planet's interior remains hot from radioactive decay and leftover formation heat, molten rock rises toward the surface, bringing with it dissolved gases that eventually escape through volcanic vents. The James Webb Space Telescope can potentially detect signs of active volcanism on exoplanets by identifying specific gas combinations that are characteristic of volcanic outgassing, such as sulfur dioxide, hydrogen sulfide, and carbon dioxide. Earth's own atmosphere is a textbook example of a secondary atmosphere. Our planet likely had a primary atmosphere of hydrogen and helium shortly after formation, but these gases were quickly lost to space. The atmosphere we breathe today originated primarily through volcanic outgassing over billions of years, with some components later modified by biological activity. Webb's study of exoplanet secondary atmospheres essentially allows us to see different versions of this process playing out around other stars, helping us understand if Earth's atmospheric evolution was typical or unusual. The rate of volcanic outgassing on a planet depends crucially on its internal heat and geological activity. Larger rocky planets tend to retain their internal heat longer than smaller ones, potentially sustaining volcanic activity and thus atmospheric replenishment for extended periods. Webb's observations of super-Earth atmospheres are helping confirm this relationship, showing that larger rocky worlds often maintain more substantial atmospheres partially due to their more vigorous and longer-lasting volcanic activity. Impacts from asteroids and comets represent another important source of secondary atmosphere components, particularly volatile substances like water. During the early history of most planetary systems, bombardment rates were much higher than today, delivering significant quantities of water, carbon compounds, and other volatiles to planetary surfaces. While Webb cannot directly observe these ancient impact events, it can detect their cumulative effects in the current atmospheric composition of exoplanets, particularly by measuring the abundance of water and organic molecules that may have been partially delivered through impacts. One of the most fascinating aspects of secondary atmospheres that Webb is investigating involves the relationship between geological activity and long-term atmospheric stability. On Earth, the carbon silicate cycle acts as a planetary thermostat. Volcanic activity releases carbon dioxide, which is eventually removed through weathering of silicate rocks, the rate of removal increasing at higher temperatures. This negative feedback loop has helped maintain Earth's climate stability over geological timescales. Webb's atmospheric observations may reveal whether similar stabilizing cycles exist on other rocky worlds, providing crucial insights into their long-term habitability. Secondary atmospheres also typically show distinctive chemical signatures that Webb can detect. While primary atmospheres have compositions similar to their host stars, primarily hydrogen and helium, secondary atmospheres show enrichment in elements and compounds that reflect their volcanic or impact origins. Elevated levels of carbon dioxide, sulfur compounds, water vapor, and nitrogen species often indicate a secondary atmosphere. The relative abundances of these gases can reveal important information about the planet's internal composition and geological history. Isotopic ratios provide another powerful tool for distinguishing primary from secondary atmospheres. Different isotopes of the same element often become fractionated, separated based on their slightly different physical properties, during processes like atmospheric escape or volcanic outgassing. Webb's high-resolution spectroscopy can potentially detect these isotopic differences, providing another line of evidence for atmospheric origin. For example, an atmosphere enriched in heavier isotopes of hydrogen or nitrogen likely experienced significant escape of the lighter isotopes, indicating a long history of atmospheric processing. The study of secondary atmospheres has profound implications for our search for habitable worlds. While primary hydrogen-helium atmospheres create surface conditions too extreme for life as we know it, secondary atmospheres, particularly those dominated by nitrogen, carbon dioxide, and water vapor like Earth's, can potentially create suitable conditions for life. A planet's ability to develop and maintain a secondary atmosphere may therefore be a crucial prerequisite for habitability, making Webb's investigations in this area particularly valuable for identifying promising candidates for future studies. The relationship between secondary atmospheres and potential habitability extends beyond just their composition. The same geological activity that generates these atmospheres, particularly plate tectonics, also helps regulate surface conditions over long timescales through processes like the carbon silicate cycle mentioned earlier. Webb's atmospheric observations thus provide indirect evidence about a planet's geological activity, offering important clues about its potential to maintain stable, habitable conditions over the billions of years potentially necessary for complex life to evolve. While studying the origins of secondary atmospheres reveals much about a planet's geological history, these investigations frequently encounter a common observational challenge: clouds and hazes. These atmospheric features represent both fascinating subjects of study in themselves and significant obstacles to observing the lower atmospheric layers that often contain the most valuable information about a planet's condition. Clouds and hazes in exoplanet atmospheres differ fundamentally from the familiar water clouds we experience on Earth. On hot exoplanets, clouds might consist of vaporized rock, molten iron, or exotic minerals like perovskite. Even on temperate worlds, cloud composition varies tremendously depending on the planet's specific chemistry. The James Webb Space Telescope can identify these diverse cloud-to-cloud compositions through their distinctive spectral signatures, revealing an astonishing diversity of atmospheric conditions across the exoplanet population. From an observational perspective, clouds and hazes create a particular challenge because they effectively block our view of the lower atmosphere. When performing transit spectroscopy, light from the host star can only probe atmospheric regions above the cloud deck. If clouds form at high altitudes, they create a spectral muting effect that weakens or completely obscures absorption features from gases in the lower atmosphere. This obstruction has frustrated many early attempts to characterize potentially habitable worlds, as high-altitude clouds prevent Webb from detecting water vapor or other biosignature gases that might exist below the cloud layer. What makes these features especially challenging is their variability. Unlike the bulk atmospheric composition, which typically remains stable over observational timescales, cloud patterns can change dramatically between observations. A planet that shows clear skies during one transit might develop extensive cloud cover by the next observation months later. This variability requires scientists to develop sophisticated statistical approaches that can account for changing cloud conditions when combining data from multiple observations. The physics behind cloud formation on exoplanets involves complex interactions between temperature, pressure, atmospheric circulation, and composition. Clouds form when atmospheric gases reach a temperature and pressure where they can condense from vapor to liquid or solid form. The specific conditions required depend on the chemical species involved. Water condenses at much lower temperatures than, for example, silicates or metallic compounds. By carefully analysing where clouds appear in an atmosphere, Webb can indirectly measure the temperature-pressure profile of planets too distant to study directly. Hazes represent a related but distinct phenomenon from clouds. While clouds form through condensation, hazes typically develop through photochemistry, chemical reactions driven by the star's ultraviolet radiation. When high-energy photons strike certain molecules in the upper atmosphere, they can trigger complex reactions that produce small solid particles that remain suspended in the atmosphere. These photochemical hazes are often composed of complex organic compounds, making them particularly interesting from an astrobiological perspective despite their obscuring effects on observations. One of the most intriguing aspects of exoplanet clouds and hazes is how they influence a planet's climate and potential habitability. Cloud layers can dramatically alter how a planet absorbs and reflects starlight, potentially cooling planets that would otherwise be too hot or warming worlds that might otherwise freeze. The James Webb Telescope can measure this effect by observing how the planet's brightness changes at different wavelengths as it orbits its star, revealing the reflective properties of its clouds and their impact on an energy balance. Scientists have developed clever techniques to work around the observational challenges posed by clouds and hazes. One approach involves focusing on wavelengths where the atmosphere is relatively transparent, allowing observations to probe deeper layers despite cloud cover. Another strategy targets the clouds themselves as objects of study, analysing their composition, altitude, and global distribution to learn about atmospheric circulation patterns and chemistry. Some research teams use machine learning algorithms to separate cloud signals from the underlying atmospheric features, extracting more information than would be possible with conventional analysis. The frequency and nature of clouds on different types of exoplanets is revealing intriguing patterns. Super-Earths and mini-Neptunes often show evidence of high-altitude clouds or hazes, while some hot Jupiters display surprisingly clear atmospheres that allow observations to reach much deeper atmospheric layers. These patterns are helping scientists develop a more comprehensive understanding of how atmospheric dynamics change with planets' size, temperature, and composition. Webb's broader infrared coverage compared to previous telescopes provides particular advantages for distinguishing between different types of clouds and hazes based on their spectral properties. For potentially habitable planets, clouds might play an especially crucial role. On Earth, clouds regulate temperature, transport water around the globe, and create the precipitation necessary for land-based life. Webb's observations of clouds on temperate exoplanets could indicate whether similar hydrological cycles might exist on these distant worlds. The telescope can potentially detect seasonal variations in cloud cover that would suggest weather patterns somewhat analogous to Earth's, though with potentially very different specific mechanisms and compositions. Understanding clouds and hazes represents one of the most active areas of exoplanet research precisely because they sit at the intersection of so many fundamental processes: atmospheric chemistry, climate dynamics, observational challenges, and potential habitability implications. Each new Webb observation adds another piece to this complex puzzle, gradually building a more complete picture of these fascinating atmospheric features and how they shape the environments of worlds throughout our galaxy. While exoplanet clouds present observational challenges for atmospheres around stars, a completely different category of planetary objects offers unique opportunities for atmospheric studies: orphan planets. Also called rogue or free-floating planets, these are planetary mass objects that wander through interstellar space without orbiting any star. Far from being astronomical curiosities, these nomadic worlds may actually outnumber conventional planets in our galaxy, potentially representing a vast population of objects with unique atmospheric properties. Orphan planets form through several possible mechanisms. Some likely developed like normal planets around stars but were subsequently ejected through gravitational interactions with other planets in their systems. Others may have formed in isolation, condensing directly from smaller pockets of the same molecular clouds that form stars, but without gathering enough mass to ignite fusion in their cores. Regardless of origin, these worlds follow solitary paths through the galaxy, carrying atmospheres that evolve under very different conditions than those of their starbound counterparts. The James Webb Space Telescope has particular advantages for studying orphan planets compared to earlier instruments. Without the overwhelming glare of a nearby host star, Webb can directly image these objects and analyze their atmospheric emission spectra with relative ease. While still challenging due to their faintness and the difficulty of distinguishing them from very distant brown dwarfs, Webb's exceptional sensitivity and spectroscopic capabilities make it the first observatory truly capable of characterizing orphan planet atmospheres in detail. What makes orphan planet atmospheres scientifically valuable is precisely their isolation from stellar influences. Without intense stellar radiation driving atmospheric chemistry, photodissociation, or escape, these atmospheres preserve conditions that may reflect their primordial composition. They essentially function as time capsules, potentially revealing the original makeup of the protoplanetary disks from which they formed. Webb's spectroscopic observations can determine whether these atmospheres retain higher abundances of lightweight elements like hydrogen and helium that are quickly lost from planets close to stars. The thermal properties of orphan planets create particularly interesting atmospheric dynamics. Without stellar heating, these worlds rely entirely on their internal heat to drive weather and maintain temperatures above the absolute cosmic background. Younger and more massive orphan planets retain significant heat from their formation, which gradually radiates away over billions of years. Webb can measure this thermal emission, essentially taking the temperature of these isolated objects and determining how their atmospheres transport and retain heat without external energy input. Despite their isolation, orphan planets aren't entirely without energy sources that can drive atmospheric chemistry. Many likely maintain significant internal heat from radioactive decay and slow gravitational contraction. This heat can drive convection and complex atmospheric circulation patterns. For larger orphan planets with masses approaching brown dwarf status, limited deuterium fusion might occur in their cores, providing additional energy. Webb's infrared sensitivity is ideal for studying these internal, energy-driven processes through their effects on atmospheric temperature structure. One of the most surprising discoveries about orphan planets is that some may maintain conditions conducive to certain forms of life despite their lack of a star. Gas giant orphan planets might harbour moons large enough to maintain subsurface oceans heated by tidal forces, creating potential habitats similar to moons like Europa in our solar system. While Webb cannot directly image such moons, it can characterize the atmosphere and thermal properties of the host planets, helping assess whether they could sustain satellite systems with potentially habitable conditions. Atmospheric chemistry on orphan planets follows different pathways than on irradiated worlds. Without photochemistry driving reactions in the upper atmosphere, chemical processes are primarily driven by temperature, pressure, and catalytic interactions. Webb's spectroscopic capabilities allow scientists to analyse which molecular species predominate in these environments. Early observations suggest more abundant methane and ammonia compared to irradiated planets, where ultraviolet light would typically destroy these molecules, along with more complex hydrocarbons that would be dissociated in high radiation environments. The boundaries between what constitutes an orphan planet versus a failed star, brown dwarf, remain somewhat blurry, with mass being the primary distinguishing factor. Objects below about 13 Jupiter's masses cannot sustain deuterium fusion and are generally classified as planets regardless of how they formed. Webb's ability to measure both atmospheric composition and thermal properties helps astronomers place ambiguous objects into their proper categories, refining our understanding of how these populations overlap and how their formation mechanisms might differ. The population statistics of orphan planets remain highly uncertain, but some estimates suggest they might outnumber stars in the Milky Way. If true, this would mean that the majority of planetary mass objects in our galaxy don't orbit stars at all. The James Webb Telescope is conducting deep field surveys specifically designed to detect these faint, isolated objects, gradually building a census of the orphan planet population. By characterizing the atmospheres of orphan planets across different mass ranges and estimated ages, scientists can construct a more complete picture of their formation, evolution, and potential for harboring subsurface habitable environments. The study of orphan planet atmospheres connects to broader questions about planetary evolution throughout the galaxy. By comparing atmospheres of orphan planets with those of planets still orbiting stars, scientists can isolate exactly how stellar radiation influences atmospheric development. This comparative approach provides a control group of sorts for atmospheric studies, helping disentangle which features of conventional exoplanet atmospheres are intrinsic to the planets themselves versus imposed by their stellar environments. Each new orphan planet characterized by Webb thus serves as a crucial data point in our broader understanding of planetary atmospheres throughout the galaxy. The study of orphan planets expands our understanding of atmospheric processes in isolation from stellar influence, but for the vast majority of planets orbiting stars, the connection between atmospheric composition and climate remains a critical focus of the James Webb Space Telescope's investigations. Climate and atmosphere are so deeply interconnected that studying one inevitably reveals insights about the other, creating a holistic picture of how these complex systems function on distant worlds. Atmospheric composition forms the foundation of any planet's climate system. Different gases absorb and emit radiation at specific wavelengths, directly controlling how energy moves through the system. The James Webb Space Telescope's spectroscopic capabilities allow scientists to identify and quantify key climate-regulating gases like water vapour, carbon dioxide and methane in exoplanet atmospheres. These greenhouse gases function essentially as a planetary thermostat, trapping infrared radiation that would otherwise escape to space and warming the planet's surface. The concentration of these gases dramatically affects a planet's surface temperature, potentially making the difference between a frozen wasteland and a temperate, habitable world. Webb can detect the presence and relative abundance of these gases, providing crucial inputs for climate models. For instance, early Webb observations have identified carbon dioxide in multiple exoplanet atmospheres, allowing scientists to estimate its warming contribution based on its concentration and the total atmospheric pressure. Beyond simple composition, the vertical structure of an atmosphere fundamentally shapes its climate. Atmospheres typically organize into distinct layers with different temperatures and compositions, similar to Earth's troposphere, stratosphere, mesosphere, and thermosphere. The James Webb Telescope can construct temperature profiles of exoplanet atmospheres by analyzing how absorption features change across different wavelengths, which probe different atmospheric depths. These temperature profiles reveal crucial information about heat transport within the atmosphere and the presence of weather-driving temperature gradients. Atmospheric circulation represents another critical component of climate that Webb can indirectly measure. As a planet rotates, complex patterns of winds develop that redistribute heat from warmer to cooler regions. On tidally locked planets that always present the same face to their star, This circulation becomes especially important, potentially making the difference between a habitable world and one with a permanently frozen night side. By measuring temperature differences between a planet's day and night sides during different phases of its orbit, Webb can assess how efficiently its atmosphere distributes heat, providing insights into global wind patterns and circulation cells. Clouds play a particularly complex role in climate regulation, both reflecting incoming stellar radiation and trapping outgoing heat. The James Webb Telescope's ability to detect cloud layers at different altitudes and composed of different materials allows scientists to incorporate these effects into climate models. Some exoplanets show evidence of highly reflective cloud layers that significantly cool their dayside temperatures, while others have high-altitude haze layers that create strong greenhouse effects. The specific composition of clouds, whether water ice, carbon dioxide ice, silicates, or more exotic materials, dramatically affects their radiative properties and thus their climate impact. The relationship between atmospheric mass and climate stability represents another important connection Webb is helping to clarify. Planets with thicker atmospheres generally experience less extreme temperature variations as the greater mass of air can store and transport more heat. This buffering effect is particularly important for planets with eccentric orbits that experience varying stellar intensity, or for slowly rotating worlds with long day-night cycles. Webb's ability to constrain atmospheric thickness by measuring spectral feature shapes provides insights into this climatic stability. Seasonal variations offer another window into exoplanet climate systems. While detecting seasons on distant worlds pushes the limits of current technology, Webb can potentially identify seasonal changes in atmospheric composition or cloud patterns for certain favourable targets. For instance, changes in carbon dioxide concentration might indicate seasonal cycles of plant growth and decay on potentially habitable worlds, while variations in methane might signal seasonal changes in geological or potentially biological activity. Even without detecting specific molecular changes, identifying systematic temperature variations as a planet orbits can reveal the presence of axial tilt and resulting seasonal patterns. The climate-atmosphere connection extends to questions of long-term stability crucial for habitability. On Earth, the carbon silicate cycle acts as a planetary thermostat that has maintained relatively stable conditions over billions of years, despite the Sun's increasing luminosity. While Webb cannot directly observe such geological processes, it can identify atmospheric signatures that suggest similar feedback mechanisms might be operating on other worlds. For instance, the ratio of carbon dioxide to other gases in a planet's atmosphere provides clues about whether regulatory cycles might be active. Water plays a particularly critical role in climate regulation, existing in all three phases, solid, liquid and gas, within the temperature ranges relevant for habitability. Webb can detect water vapour in exoplanet atmospheres, and in some cases might even identify signatures of surface oceans through their effects on a planet's reflectivity and thermal properties. The presence of substantial water indicates potential for climate-stabilizing processes like cloud formation, precipitation, and ocean heat storage that could maintain conditions suitable for life. One of the most fascinating aspects of the atmosphere-climate connection is how dramatically different these systems can be from planet to planet. Some worlds might have global-scale storm systems that dwarf Jupiter's Great Red Spot PIM, while others might experience rain of molten glass or iron. By studying atmospheric composition and thermal patterns across a diverse range of exoplanets, Webb is revealing the incredible variety of climate systems that can develop under different conditions of mass, composition, stellar irradiation, and rotation rate. Each new observation adds another data point to this comparative climatology, helping scientists develop more comprehensive theories of how planetary atmospheres and climates evolve and function. While the transit method provides our primary window into exoplanet atmospheres, it has an important limitation. It only samples the thin ring of atmosphere at the planet's terminator, the boundary between day and night sides. To overcome this limitation and develop a more complete picture of exoplanet atmospheres, astronomers employ another powerful technique made possible by the James Webb Space Telescope: secondary eclipse observations. A secondary eclipse occurs when a planet passes behind its star from our perspective. Just before disappearance, we observe the planet's fully illuminated day side. When the planet slips behind the star, its light contribution is temporarily removed from the total system light. By carefully measuring the tiny drop in infrared brightness, typically just tens to hundreds of parts per million, Webb can isolate the thermal emission coming directly from the planet's day-side atmosphere. This technique complements transit observations perfectly. While transits reveal the composition of the terminator region by showing which wavelengths are absorbed as light passes through the atmosphere, secondary eclipses show which wavelengths are emitted by the hot day side of the planet. Together, these two perspectives allow scientists to build a more comprehensive model of the planet's atmospheric structure, composition, and temperature distribution. Secondary eclipse observations are particularly valuable for studying atmospheric temperature structure. Different wavelengths of the infrared light originate from different depths in the atmosphere, with shorter wavelengths typically coming from deeper, hotter layers and longer wavelengths emerging from cooler, higher altitudes. By measuring how the planet's emission spectrum changes across wavelengths, Webb can essentially construct a vertical temperature profile, determining whether the atmosphere has a temperature inversion, where upper layers are hotter than lower ones, how steeply temperature changes with altitude, and whether distinct atmospheric layers exist. The James Webb Space Telescope's exceptional sensitivity in the mid-infrared range makes it uniquely capable of performing high-quality secondary eclipse observation. This wavelength range is particularly important because it contains the peak thermal emission for many warm to hot exoplanets. Webb's MIRI instrument can capture this emission with unprecedented precision, revealing far more detail than was possible with previous observatories. Secondary eclipse measurements also provide our best window into understanding the energy budget of exoplanets, how much stellar energy they absorb versus how much they reflect or irradiate. This balance fundamentally determines a planet's climate. By comparing the planet's dayside temperature, measured during secondary eclipse, with the amount of stellar energy it receives, scientists can determine its albedo, how reflective its atmosphere or surface is. Highly reflective planets with substantial cloud cover will have much cooler daysides than dark Sia, or cloud-free worlds receiving the same amount of stellar radiation. One particularly valuable aspect of secondary eclipse observations is their ability to detect thermal emission from relatively cool planets, potentially even those in habitable zones. While direct imaging struggles to separate the faint light of temperate planets from their much brighter host stars, secondary eclipse techniques can potentially detect the infrared glow of these worlds by measuring the tiny difference in system brightness when they slip behind their stars. This capability may eventually allow Webb to study the atmospheric properties of potentially habitable worlds that are otherwise difficult to characterize. Secondary eclipse spectroscopy has already revealed fascinating features in exoplanet atmospheres. For hot planets, it can detect the presence of molecules like water vapor, carbon monoxide, and the carbon dioxide through their emission features rather than absorption. It can also identify emission inversions, where certain molecular features appear in emission rather than absorption, indicating the presence of a thermal inversions in the atmosphere. These inversions, somewhat similar to Earth's stratosphere but often more extreme, typically form when gases in the upper atmosphere absorb starlight directly, creating a layer that's hotter than the levels below. The timing of the secondary eclipse also provides valuable information about a planet's orbit. By precisely measuring when the eclipse occurs compared to when it's predicted based on the transit timing, scientists can determine whether the planet's orbit is circular or eccentric. This orbital information is crucial for understanding the planet's tidal heating, climate stability, and potential habitability. For planets that are very hot, such as hot Jupiters orbiting extremely close to their stars, secondary eclipse observations can sometimes detect light reflected from the planet in addition to its thermal emission. At shorter wavelengths where thermal emission is minimal, any detected signal during secondary eclipse likely comes from reflected starlight. This reflected component provides information about cloud cover and composition that complements the thermal emission data, building a more complete picture of the atmosphere. When combined with observations at different orbital phases, secondary eclipse data helps create temperature maps of exoplanets. By measuring how the infrared brightness changes as different portions of the day and night sides come into view, scientists can determine how temperatures vary across the planet's surface. These phase curve observations have revealed that some hot Jupiters have hotspots offset from the point directly facing the star, clear evidence of winds redistributing heat around the planet. While extraordinarily valuable, secondary eclipse observations come with significant technical challenges. The eclipse depth, how much the system brightness drops when the planet is hidden, is typically much smaller than the transit depth, requiring exceptional precision and stability from Webb's instruments. Background noise, stellar variability, and instrumental effects must be carefully accounted for to extract the planet's faint signal. Despite these challenges, Webb's design specifically incorporated features to optimize secondary eclipse science, including exceptional thermal stability and precision pointing capabilities. The combination of transit spectroscopy and secondary eclipse observations represents a powerful approach for atmospheric characterization. While transits tell us which gases are present in the terminator region, secondary eclipses reveal the temperature structure and energy balance of the day side. This complementary information allows scientists to build comprehensive models of how exoplanet atmospheres function globally, from chemical composition to energy transport to vertical structure. Each new observation adds another piece to our understanding of these distant worlds, gradually transforming them from distant points of light into real places with unique atmospheric conditions and climates. The complementary insights from transit and secondary eclipse observations reveal a complex picture of exoplanet atmospheres, but these atmospheres don't exist in isolation. They are fundamentally shaped by their host stars. As the James Webb Space Telescope continues its survey of alien atmospheres, one of the clearest patterns emerging is how profoundly different types of stars create dramatically different atmospheric environments, even for otherwise similar planets. The most obvious stellar influence comes through temperature. A planet orbiting a hot, luminous A-type star receives far more total energy than an identical planet at the same relative distance from a cool red dwarf. This basic energy difference fundamentally determines a planet's equilibrium temperature, which in turn controls which gases can exist in its atmosphere without freezing out or being completely dissociated by heat. Webb's observations confirm that atmospheric chemistry varies systematically with stellar temperature, with hotter stars generally producing more photochemically active environments where complex molecules are broken apart by intense radiation. However, total energy input tells only part of the story. The specific wavelength distribution of that energy, a star's spectrum to stipple, proves equally important for atmospheric chemistry. Different stellar types emit significantly different proportions of their energy across the electromagnetic spectrum. This spectral energy distribution critically determines which photochemical reactions dominate in a planetary atmosphere. M-dwarf stars, the most common stellar type in our galaxy, present a particularly interesting case. Despite their relatively cool temperatures, these red dwarfs emit proportionally far more of their energy as ultraviolet and X-ray radiation compared to Sun-like stars. This high-energy radiation penetrates deep into planetary atmospheres, breaking chemical bonds and triggering complex photochemical reactions. Webb observations of planets around M-dwarfs consistently show evidence of this intense photochemistry, including unusual hydrocarbon hazes and depleted methane levels that result from these high-energy photochemical processes. Perhaps the most dramatic stellar impact comes through eruptive events like flares and coronal mass ejections. M-dwarf stars are notorious for frequent powerful flares that can temporarily increase their ultraviolet output by factors of hundreds or even thousands. Webb has observed the atmospheric effects of these flaring events by taking spectroscopic measurements before, during, and after flares. The data reveals how these energy bursts can dramatically accelerate atmospheric escape, potentially stripping away significant portions of an atmosphere over geological timescales. This observation has profound implications for habitability around the galaxy's most common stars, suggesting that planets need extraordinary protection mechanisms like powerful magnetic fields to maintain stable atmospheres in these hostile stellar neighborhoods. Stellar composition also directly influences planetary atmospheric chemistry by determining which elements are available during planet formation. Stars with higher metallicity, astronomical jargon for elements heavier than hydrogen and helium, produce planets with correspondingly metal-rich atmospheres. Webb's spectroscopic capabilities can detect these compositional differences, revealing how elements like carbon, oxygen, and nitrogen in planetary atmospheres correlate with their abundances in the host star. This relationship provides important constraints on planet formation models and helps scientists distinguish between primary atmospheres captured from the protoplanetary disk versus secondary atmospheres generated through later processes like outgassing. The age of a star represents another crucial factor shaping planetary atmospheres. Young stars emit significantly more high-energy radiation than their older counterparts of the same mass. planets orbiting young stars, this therefore experienced much more intense atmospheric stripping and photochemistry early in their history. Webb can identify signatures of this evolutionary effect by comparing atmospheres of similar planets around stars of different ages. This comparison reveals how atmospheric composition changes over billions of years as both the planet and star evolve, information crucial for understanding Earth's own atmospheric history and the potential habitability of exoplanets at different evolutionary stages. Binary and multiple star systems create particularly complex atmospheric environments. Planets in these systems experience varying radiation patterns as they orbit, sometimes receiving dramatically different energy inputs as their orientation to multiple stars changes. Webb has observed several planets in binary systems, revealing how these complex radiation environments create unusual atmospheric chemistry and circulation patterns. In some cases, the combined radiation from multiple stars can drive atmospheric escape rates far beyond what a single star would produce, potentially limiting the long-term stability of atmospheres in these systems. The stellar impact extends beyond just radiation to include stellar winds, streams of charged particles that interact with planetary atmospheres. These winds can physically strip away atmospheric gases, particularly from planets with weak magnetic fields. By measuring the rate of atmospheric loss from similar planets around different stellar types, Webb is quantifying how stellar wind properties correlate with atmospheric erosion rates. This data helps scientists determine which types of stars are most likely to host planets with stable, long-lived atmospheres conducive to life. Perhaps the most profound stellar influence concerns habitability itself. The boundaries of the traditional habitable zone, where liquid water could exist on a planet's surface, depend directly on stellar properties. Hotter stars have habitable zones farther out, while cooler stars have them much closer in. Webb's atmospheric characterization of planets across different stellar types is refining our understanding of how these habitable zones function in practice, revealing that factors like stellar activity and spectral energy distribution can significantly modify the theoretical boundaries. These observations suggest that the concept of stellar habitability is far more nuanced than previously thought, with each stellar type offering unique advantages and challenges for potential life. The relationship between stars and planetary atmospheres represents a crucial factor in our search for habitable worlds. As Webb continues to characterize more systems, it's becoming increasingly clear that understanding a planet's atmosphere requires intimate knowledge of its host star as well. These insights are helping astronomers prioritize which planetary systems offer the most promising environments for detailed studies of potentially habitable conditions. While the James Webb Space Telescope collects unprecedented observational data about exoplanet atmospheres, converting these raw measurements into scientific understanding requires another crucial element: sophisticated computational modeling. Behind every atmospheric discovery lies a complex ecosystem of models that help scientists interpret data, test hypotheses, and extract the maximum information from Webb's observations. The raw data from Webb doesn't directly provide a list of atmospheric gases or a temperature profile. Instead, it delivers spectra, patterns of light intensity across different wavelengths that contain encoded information about atmospheric properties. Computational models are essential tools for decoding these spectral patterns and converting them into meaningful physical and chemical properties. These models incorporate fundamental physics and chemistry to simulate how light interacts with different atmospheric components, creating predicted spectra that can be compared with Webb's actual observations. At the heart of this modelling effort are radiative transfer models, which simulate how radiation moves through an atmosphere, accounting for absorption, emission, and scattering by various molecules and particles. These models require extensive databases of molecular absorption properties, essentially dictionaries of how each possible atmospheric component interacts with light at different wavelengths. Many of these molecular properties must be measured in laboratories under conditions mimicking alien atmospheres, with high temperatures and exotic chemical combinations that don't naturally occur on Earth. The process typically begins with forward modelling, where scientists create simulated atmospheres with various compositions, temperatures, and structures, then calculate what spectrum Webb would observe if that model were correct. By comparing thousands of these simulated spectra with the actual observation, they can identify which models provide the closest match, revealing the most likely atmospheric properties. This approach becomes increasingly powerful as Webb observes more planets, allowing scientists to identify patterns and refine their models based on a growing database of real-world examples. Bayesian statistical techniques represent a particularly powerful approach for atmospheric modelling. Rather than simply finding a single best-fit model, Bayesian methods explore the full range of possible atmospheric scenarios compatible with the data, assigning probabilities to different possibilities. This approach honestly addresses the inherent uncertainties in the observations and provides a more complete picture of what we know and don't know about an exoplanet's atmosphere. For instance, instead of claiming this planet has exactly 3% water vapour, a Bayesian analysis might conclude the water vapour concentration is between 1 and 5% with 95% confidence. The complexity of these models cannot be overstated. They must account for dozens of potential atmospheric gases, each with unique spectroscopic signatures that can overlap and interfere with each other. They incorporate vertical temperature structures that change how gases absorb and emit at different atmospheric layers. They include the effects of clouds and hazes, with various compositions and particle sizes, and they must address numerous confounding factors like instrument system attacks, stellar activity, and contamination from interstellar dust. Creating models that handle all these factors while remaining computationally feasible represents a significant scientific achievement in itself. Machine learning and artificial intelligence are increasingly complementing traditional physical models in atmospheric analysis. These approaches can identify patterns in spectroscopic data that might not be obvious to human researchers or standard analysis techniques. Neural networks trained on thousands of simulated planetary spectra can rapidly classify new observations or flag unusual features that warrant deeper investigation. These AI-assisted techniques are particularly valuable given the enormous volume of data Webb is collecting, allowing researchers to quickly identify the most promising targets for more detailed analysis. One of the most important principles in exoplanet atmospheric modelling is the use of multiple independent approaches. Different research teams often develop their own modelling frameworks with different underlying assumptions and computational techniques. When diverse modelling approaches converge on similar atmospheric properties for a given planet, scientists gain confidence in those results. Conversely, when different models yield conflicting interpretations, this highlights areas where additional observations or theoretical development is needed. This multi-model approach helps guard against the risk of reaching incorrect conclusions based on the limitations of any single modelling technique. Atmospheric models also play a crucial role in planning Webb's observations. Before telescope time is allocated, scientists use models to predict which planets will have detectable atmospheric features and which observing modes and wavelength ranges will provide the most valuable information. These predictions help optimize the use of limited telescope time by focusing on observations with the highest scientific return. As data from early observations feeds back into improved models, this planning process becomes increasingly refined, allowing more efficient use of Webb's capabilities throughout its mission lifetime. The modelling process faces particular challenges when addressing potentially habitable planets. The atmospheres of temperate, Earth-sized worlds are especially difficult to detect and characterise due to their relatively small size and cool temperatures. Models must be exquisitely sensitive to extract the subtle signals of these atmospheres from Webb's data. Additionally, habitability assessment requires modelling not just the current atmospheric state, but its stability over geological timescales, how it responds to the changes in stellar output, geological activity, and potential biological influences. These long-term evolutionary models incorporate atmospheric chemistry, climate dynamics, and planetary interior processes into comprehensive simulations of how habitable conditions might emerge and persist. One particularly powerful modelling approach involves comparative planetology, using the known properties of solar system planets to inform our understanding of exoplanets. Models calibrated against Venus, Earth, Mars, and the gas giants provide crucial reality checks for exoplanet interpretations. When Webb observes an exoplanet with properties similar to a solar system world, models can leverage our much more detailed knowledge of these nearby planets to make more confident predictions about the exoplanet's nature. This comparative approach helps bridge the gap between the limited information available for distant worlds and our deeper understanding of planets we've studied up close. The interplay between observations and models creates a virtuous cycle of scientific progress. Initial Webb observations inform preliminary models, which identify the most important additional measurements needed. These new observations then refine the models, gradually building a more comprehensive understanding of exoplanet atmospheres. This iterative approach allows scientists to extract far more information from Webb's data than would be possible from a simple analysis of individual observations in isolation. Perhaps most importantly, computational models transform Webb's spectroscopic data from abstract patterns of light into concrete understanding of alien worlds. They allow scientists to translate lines on a graph into vivid, physically meaningful descriptions, determining whether a planet has rain clouds, strong winds, or potential signs of life. They connect abstract measurements to fundamental questions about how planets form, evolve, and potentially become habitable. As Webb continues its mission, these increasingly sophisticated models will be essential tools for translating its revolutionary observations into profound new insights about the diversity of atmospheres throughout our galaxy. The sophisticated computational models used to interpret Webb's data don't just reveal the current state of exoplanet atmospheres, they also help scientists reconstruct how these atmospheres evolved over billions of years. This long-term perspective has unveiled one of the most fascinating processes in planetary science: natural terraforming, the gradual transformation of initially inhospitable worlds into potentially habitable environments through natural processes that unfold over geological timescales. Natural terraforming represents a profound shift in how we think about habitability. Rather than viewing it as a fixed property that a planet either has or lacks, Webb's observations support the view that habitability can emerge gradually through atmospheric evolution. Many planets that form with hostile conditions may naturally develop more life-friendly environments over time through a series of chemical, geological, and potentially biological processes that transform their atmospheres. Earth's own history provides the clearest example of this process. Our planet's early atmosphere contained virtually no oxygen and would have been toxic to most life forms familiar to us today. Over billions of years, the emergence of photosynthetic organisms gradually filled the atmosphere with oxygen, eventually creating conditions that allowed complex multicellular life to evolve. The James Webb Space Telescope is now helping scientists determine whether similar transformations might be common throughout the galaxy by identifying planets at different stages of this evolutionary process. One of the most important natural terraforming mechanisms identified through Webb's observations involves the gradual oxidation of planetary atmospheres. Young planets often form with reducing atmospheres rich in hydrogen, methane, and ammonia, gases that would be toxic to Earth-like life. Over time, processes like ultraviolet photolysis, the breaking of chemical bonds by starlight, and the escape of lightweight hydrogen to space can gradually transform these reducing atmospheres into more oxidized ones, containing carbon dioxide, nitrogen, and potentially oxygen. Webb can track this progression by identifying planets with atmospheres in various stages of oxidation, from primordial hydrogen-rich envelopes to more processed atmospheres showing evidence of oxidized gases. The carbonate-silicate cycle represents another crucial natural terraforming process that Webb is helping to identify in exoplanet atmospheres. This cycle, which helps regulate Earth's climate over geological timescales, involves the weathering of silicate rocks by rainwater containing dissolved carbon dioxide. This process removes carbon dioxide from the atmosphere, eventually depositing it as carbonate minerals in ocean sediments. Volcanic activity later returns this carbon to the atmosphere, completing the cycle. Webb can detect signatures of this process by measuring the relative abundances of carbon dioxide and other gases, providing evidence for active geological cycles that could help regulate a planet's climate over the long term. Water delivery represents a third key aspect of natural terraforming. Many planets may form relatively dry, but later receive water through asteroid and comet impacts. Webb can identify evidence of such water delivery by detecting hydrogen and oxygen species in atmospheres and comparing their isotopic ratios, which often carry signatures of their origin. Observations of cometary material in exoplanet atmospheres would suggest that water delivery through impacts might be a common process, potentially increasing the number of worlds that develop conditions suitable for life over time. The gradual cooling of a planet's interior also plays a role in natural terraforming by changing the rate and composition of volcanic outgassing. Young planets with hot interiors typically experience intense volcanic activity that releases large amounts of sulfur dioxide, hydrogen sulfide, and other gases that create hostile surface conditions. As a planet cools, this volcanism typically becomes less intense, and shifts toward more carbon dioxide-dominated emissions, potentially creating more moderate conditions. Webb can track this evolution by identifying chemical signatures of different volcanic regimes in exoplanet atmospheres. Perhaps most intriguingly, Webb is searching for evidence of biological terraforming, how life itself might transform planetary environments to become more habitable for itself. On Earth, photosynthetic organisms dramatically altered our atmosphere by producing oxygen, which eventually formed an ozone layer that protects the surface from harmful ultraviolet radiation. While definitively identifying biological signatures remains challenging, Webb can potentially detect unusual chemical disequilibria that might indicate biological activity. The presence of gases like oxygen and methane together, which would quickly react and disappear without continuous replenishment, could suggest active biological terraforming. The timeframes for natural terraforming appear highly variable based on Webb's observations of planets at different evolutionary stages. Some worlds might develop potentially habitable conditions within a few 100 million years, while others might require billions of years of processing to reach similar states. This timeline depends on factors like the planet's initial composition, its distance from its star, the star's properties, and whether the planet has active plate tectonics to drive geological cycles. By studying planets of different ages, Webb is helping construct a timeline of how atmospheric habitability typically evolves. Interestingly, Webb's data suggests that natural terraforming processes might create windows of habitability rather than permanent states. As stars evolve and gradually become brighter, planets that start out frozen might enter habitable temperature ranges only to eventually become too hot as their star continues to brighten. This perspective suggests that habitability might be a relatively temporary phase in a planet's life cycle, with implications for how common we might expect habitable worlds to be at any given time in cosmic history. The study of natural terraforming highlights the dynamic nature of planetary habitability. Rather than simply categorizing worlds as habitable or uninhabitable, Webb's atmospheric investigations reveal a continuum of conditions that evolve over time. This perspective significantly expands the potential timeframes and locations where life might exist in the universe, suggesting that even worlds that start with hostile conditions might naturally develop more life-friendly environments given sufficient time for atmospheric evolution. These insights into natural terraforming processes represent just the beginning of what promises to be one of the most fascinating areas of exoplanet science in the coming decades. As Webb continues its survey of alien atmospheres, it's building a foundation for future observatories that will take this research to even greater heights. The future of exoplanetary atmosphere research extends well beyond the James Webb Space Telescope, with ambitious plans for next-generation observatories that will build upon Webb's groundbreaking discoveries. While the James Webb Space Telescope represents a tremendous leap forward in our abilities to study exoplanet atmospheres, it also has inherent limitations. Future observatories are being designed specifically to overcome these constraints and push our observational capabilities even further. The knowledge gained from Webb is directly shaping the design of these next-generation instruments, ensuring they target the most critical unanswered questions and employ the most effective observational strategies. One of the most ambitious concepts for future exoplanet characterization is the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, or similar large space telescopes with apertures potentially 2 to 3 times larger than Webb's. These observatories would collect significantly more light, allowing them to study fainter targets and obtain higher resolution spectra. This increased light-gathering power would be particularly valuable for studying Earth-sized planets in habitable zones, where atmospheric signals are extremely faint and challenging to detect even with Webb's capabilities. Perhaps the most revolutionary advancement in future observatories will be the widespread implementation of coronagraphs and starshades, technologies designed to block out the overwhelming light from host stars. While Webb has limited coronagraphic capabilities, future missions will employ far more advanced versions of these technologies. Dedicated starshade missions might even position large flower-shaped occulters tens of thousands of kilometers away from a telescope to create a perfect artificial eclipse of target stars. This approach could potentially allow direct imaging and spectroscopy of Earth-sized planets around Sun-like stars, observations that remain extremely challenging even for Webb. Direct imaging represents the holy grail for atmospheric characterization because it provides access to reflected light from a planet's atmosphere, rather than the thin ring probe during transits. This reflected light contains far more information about surface conditions and lower atmospheric layers that transit spectroscopy cannot reach. Future observatories optimized and merged for direct imaging could potentially detect continents, oceans, and even vegetation on worlds around nearby stars, providing our first true pale blue dot images of potentially Earth-like worlds. The spectral range of future observatories will likely expand beyond Webb's infrared focus to include more coverage in ultraviolet and visible wavelengths. This broader wavelength coverage will allow detection of important atmospheric features that Webb cannot see, including ozone absorption in the ultraviolet and the distinctive red edge reflectance feature that Earth's vegetation produces in the visible spectrum. Combining observations across this wider spectral range will provide more definitive characterization of atmospheric composition and potential biosignatures. Ground-based observatories will play an increasingly important role in exoplanet atmospheric research as well. The next generation of extremely large telescopes, including the 30-metre telescope, Giant Magellan Telescope, and European Extremely Large Telescope, will have primary mirrors measuring 20 to 40 metres in diameter. When equipped with advanced adaptive optics to overcome atmospheric turbulence and high-resolution spectrographs, these massive telescopes will complement space-based observations by providing extremely detailed spectra of brighter targets. Their high spectral resolution will allow them to separate exoplanet atmospheric lines from those of the Earth's atmosphere, enabling detection of specific molecular features that Webb might miss. Interferometry represents another promising technology for future atmospheric characterization. By combining light from multiple telescopes, interferometers can achieve the resolving power of a much larger telescope. Space-based interferometric arrays could potentially resolve surface features on nearby exoplanets, distinguishing between land, oceans, and atmospheric features. While technically challenging, such arrays would provide our most detailed views of exoplanets and might represent humanity's best chance to identify unmistakable signs of alien civilizations, should they exist. The computational side of atmospheric research will advance alongside these new observing capabilities. Quantum computing may eventually enable atmospheric models of unprecedented complexity, simulating chemical, physical, and potentially biological processes with a level of detail impossible with classical computers. Machine learning algorithms trained on the growing catalogue of Webb observations will become increasingly adept at identifying patterns and anomalies in atmospheric data, potentially recognizing biosignatures that human researchers might overlook. These technological advances will enable scientists to address increasingly sophisticated questions about exoplanet atmospheres. Rather than simply identifying which gases are present, future research will focus on understanding atmospheric dynamics in detail, mapping global wind patterns, tracking seasonal changes, and characterizing weather systems on worlds around other stars. For potentially habitable planets, research will increasingly focus on the stability of conditions over geological timescales, assessing whether detected environments could persist long enough for complex life to potentially evolve. The search for definitive biosignatures will drive much of this future research. While Webb can identify potential biosignatures, confirming biological origin remains challenging with current capabilities. Future observatories will search for more definitive evidence, potentially detecting combinations of gases that would be difficult to explain through non-biological processes. The ultimate goal would be detecting complex organic compounds like chlorophyll or other pigments that have specific spectroscopic signatures strongly associated with life. Perhaps most excitingly for Knowles, the statistical power of future observations will allow scientists to address big-picture questions about the prevalence and diversity of atmospheric evolution throughout the galaxy. By characterizing hundreds or thousands of exoplanet atmospheres rather than the dozens possible with Webb, researchers will identify patterns that reveal which factors most strongly influence atmospheric development. This comparative approach will help determine how common Earth-like atmospheric evolution might be in the cosmos, and what conditions most frequently lead to potentially habitable environments. The knowledge gained from the James Webb Space Telescope will serve as the essential foundation for all this future work. Webb is identifying the most promising targets for follow-up with the next-generation facilities, developing the observational techniques that future missions will refine, and building the initial catalogue of atmospheric characteristics that will inform all the future comparative studies. Most importantly, Webb's discoveries are helping scientists ask better questions. identifying the most critical gaps in our understanding that future missions should address. As we look toward this exciting future of exoplanetary atmospheric research, we can appreciate how the James Webb Space Telescope represents not an endpoint, but rather the crucial first step in a scientific journey that will continue for generations. Each new atmospheric spectra collected by Webb brings us closer to answering one of humanity's most profound questions: whether the conditions necessary for life as we know it are rare or common throughout the cosmos. The telescope's legacy will be measured not just by its own groundbreaking discoveries, but by how it paved the way for the even more remarkable revelations that will follow in the coming decades of exploration.